Hi there, welcome to this lecture on matrix algebra. This is lecture number 2, part 2. In this lecture, we'll continue our discussion on solving linear systems and related issues. Okay, let's get started. In the first part of the lecture, we talked about an algorithm that can be used to carry out and find the solution of a n times n system. So now let's ask a question. How many operations is needed to solve an n by n system? Here, when we say an operation, it means one calculation, either an addition, subtraction, multiplication, or division. So we know there are two steps we need to carry to solve this equation. And the first one is to put the matrix of coefficients in reduced row form. And here the matrix would be of size n times n plus 1. And once that is accomplished, and then we will find the solutions by a backward substitution algorithm. Okay, so let's now write out the matrix of coefficients. Here it is a n by n plus 1, so there are n rows here, and there are n plus 1 columns here in this matrix. Let's take a look at each steps we have to take to put it in a reduced row form. Let's consider step 1, where we treat column 1. So we want to do computations such that the positions under the diagonal element, all these here, shall become 0. That means in the end, after we have done with the calculation, we will get all zeros down here. Now let's take a closer look at what we do exactly and how many calculations are needed. So let's take a look at the second row. What we need to do will be, we need to multiply the first row by a number which is negative a21 over a11. And then there are n plus 1 such multiplications we need to perform. And then we'll have to add this on top of each of these. And then you don't have to do the first one because you know it's going to be 0. Actually, here you don't even need to multiply the first a11. You know it's going to be add on top and make it 0. So basically you need to do for the n remaining element from index 2 to n plus 1. Okay, so totally how many operations are needed will be exactly 2 times n. And then we repeat this for the remaining rows, the third, the fourth, and all the way to the nth row. And for each one, we do the same thing. We multiply the first row by this number, and for the n elements here, and add them on top. And this one we know it's 0, so we don't even need to do that. Okay, so for each of these rows here, the operation number is 2n, and then we have to do n minus 1 rows because we don't need to do it for the first row. So the required operation then would be 2n times n minus 1. So here we are interested in the count of number of operations when the system is very large. So that means n is a very big number. So when n is very big, then this number 1 comparing to n is very small. So n minus 1 is approximately just n. So this will give me approximately 2n square operations. Okay, so we can carry out the same counting for the row number, column number 2 and column number 3, and so on and so forth. And with the same kind of argument, we'll conclude that for column 2, it will take approximately 2 times n minus 1 square, because it's a little bit smaller an area you cover. And then for column 3, it will be approximately 2 times n minus 2 square operations. And then you probably see the pattern when you go further down, and the number of operations here will be n minus a further bigger number, like n minus 3 square, n minus 4 square, so on and so forth. Okay, so after we carry out for all the columns, we will have a reduced row matrix. And we can add up all the number of operations needed for each step to find the total number of operations. So this will be adding them up. So there is a 2, which is a common factor. We just put it out. And then what we have here will be the n square plus n minus 1 square from here, and then plus n minus 2 square from here, and so on and so forth, all the way to the very last column, which is 1 square. Okay, so we'll be adding up these n numbers. And then we see that this summation is just adding up n j square for this j integer from 1 to n. And for this summation, we know the exact form, which is this n times n plus 1 times 2n plus 1 over 6. And then again, using the fact that n is very large, so n plus 1 is just n approximately, and 2n plus 1 is just approximately 2n. You put that in, and 2 and 6 cancel out 1, so you get 3 down here, and then you get 2n cubed. There are 3 n's. Okay, so the total number of operations needed here to put a matrix to a reduced row form is approximately n cubed times a constant, that's 2 over 3. So the second step of the computation to solve the system is the backward substitution when you already have your system in triangular form, like this. So down here, below the diagonal, all the elements are 0. This is a reduced row form. So we would solve this and then plug it back into, substitute the second last one, and then you got 2 solutions, and then you keep going all the way until you finish the first one. Now let's count the number of operations. Okay, to compute this here, you need 1 operation, just bn over ann. And then to calculate the n minus 1, and you would need bn minus 1 minus this number here, and then divided by the an minus 1 in front of x. So there are 2 operations. And then you keep going backwards, and then realize that each time you go 1 step back, and the number of operations will increase by 1. So it will be 1, 2, 3, 4, all the way to n when you compute the first unknown x1. Okay, so the total number of operations is just summing over all these counts. Okay, so it's approximately 1 plus 2 plus 3 all the way to plus m. And then this is, we know, is just n times n plus 1 over 2. And then using the fact that n is large, then n plus 1 is just about n. So you get n square, approximately n square over 2. So that's what it takes to do the backward substitution. It's a constant times n square. So remember, for the step 1, the Gaussian elimination, and there we calculated that the number of count is approximately some constant times n to the power 3. So if n is a very large number, then n to the power 3 is much, much bigger than n to the power 2. So this step here is takes much less time than the first step, the Gaussian elimination. Now let's talk about the topic of choosing a good pivot. So let's recall the Gaussian elimination steps. So to treat column number 1, what we did was we will multiply the first row by A21 over A11 and then add on top of the second one. And then for the third row, it will be multiplied. The first row will be multiplied by A31 over A11. And so on and so forth. And then the last one will be AN1 over A11. Sorry, that should be AM1. It's this one. Okay, so we see that the element A11 is important because it's being divided every step. And therefore, we call this the pivot. Like you're pivoting here, and then you rely on that one, and then you make all those 0. So one obvious thing about the pivot is that A11 cannot be 0. Then you'll be dividing by 0, which is undefined. And secondly, if you divide it by A11, and if that number A11 shall be very small in absolute value, very close to 0, then that division will give you a very large number, which would lead to large computational errors. And now we later will see an example to that effect. So right now, let's talk about how to choose a good pivot. So you want to choose an A11 that is not 0, and that is not close to 0 in absolute value. And in fact, the best choice would be to pick an A11 among all possible ones that it has the largest possible absolute value. So one could go through the column 1 and find the element A such that the one that has the largest absolute value. And then let's say it's A31 has the largest absolute value. And then you switch that one. The row number 3 will be switched with row number 1 such that the new A11 will have the largest possible absolute value. And that will be our new pivot. Okay, so let's now take an example to show that when the pivot is very small, it can lead to computational errors. Let's take an extreme example. And in general, it's not so extreme, but this gives you an idea where things can go wrong. Okay, let's take a very small number. We call it epsilon, and let's take it to be 10 to the power negative 9. So that's a very small number. And now considering you're doing this in a computer or in a calculator, and the computer uses something called floating point representation of the number with certain accuracy. Let's say it can represent number that has 6 decimal digits. And then if you have 7s, then the 7th will be rounded off or chopped off. Okay. So in this case, how would you compute a 1 over epsilon? Well, 1 over epsilon, it would be now 10 to the positive 9 power, right? So which is 1, which followed with 9 zeros. And if you write this with scientific notation, this will be 1.00000 times 10 to the power 9. So in a computer, numbers are stored in this way. So it will be stored of how many decimal points here that the accuracy it allows, and then it will store the power, and that means the magnitude of the number. Although in the computer this is done in binary, and here we write it out in decimal just to illustrate the idea. It's the same kind of a difficulty we will encounter because we use finite many numbers of. Now let's see if we want to compute this value, 1 over epsilon plus 1, well, that will be this number here with one more, right? So in scientific notation, it will be 1.000000001 times 10 to the power 9. And since we can only have 6 decimal digits of accuracy in our number, then the last 001 here will be dropped, and in the computer it's approximated by this number. Okay, and that is because the last digits are chopped off. Okay, and let's also look at like epsilon plus 1. Well, that will be 1.000000000. Oh, sorry, this should be 1 here. Okay, and then you give this number to the computer, and it can only keep 6 decimal digits. So it will chop off the last 3, and you will get 1.000000. Here you see that because epsilon is extremely small, when you do 1 plus epsilon, it's just 1, and the computer cannot distinguish this number 1 plus epsilon and 1. Okay, let's keep this limitation of 6 decimal digits, and let's try to solve the system, the following system, which is epsilon x1 plus x2 equals 1, and the second equation is x1 minus x2 is 0. So we can see that what will be the exact solution. Well, x1 will have to equal to x2, and then if you put that in, then x1 and x2 will both be 1 over epsilon plus 1. Right? It will be 1 over epsilon plus 1. And then we already see that if that number is reached and in the computer, in the computation, what will it be, this number in the computer? Well, 1 plus epsilon in the computer, it will just be 1, and you will just have 1 over 1, which will be 1. So you should expect that the correct answer, if the computer gets it, it will tell you x1 equals x2 equals 1. Let's see. Now let's carry out what we called naive Gaussian elimination, meaning that we just take the equation as it is and we just pivot whatever number happens to be there. Okay, so we will pivot, the epsilon will be the pivot. Okay, so what you do, well, then you have to multiply the first equation by epsilon to the power -1, meaning 1 over epsilon, negative of that, and add on top of the second one. Now it gives me that will be 0, and then here will be -1 minus epsilon to the -1. That's what you multiplied on, and then here will be negative epsilon -1 plus 0, and that's what you get. Okay, and then these numbers in the computer, in particular this number here, as we have seen that e to the -1 will be 10 to the power 9, and -1 will not be able to be stored in the computer. So in your computer, this number will just become negative epsilon to the power -1. Okay, so now we can solve this and using backward substitution. So this becomes two equations as the follows: epsilon x1 plus x2 equal 1, and the second equation is negative epsilon -1, x2 is negative epsilon -1. So you solve for the second one, you get x2 is 1. And then if you substitute x2 equals 1, and then you have epsilon x1 is 0, and then x1 will be 0. Okay, wait a second. So you'll be wondering, what? That is the solution the computer will tell you. If we refer to what we did on the previous slides, we say that the exact solution represented in the computer should give me x1 equal 1 and x2 equal 1. And we don't get that. In particular, for x1, there's a huge error. So that shows that if you have a pivot with a very small absolute value, it can cause large errors. And let's compare this with the where we do the pivot. Okay, so let's say, can we resolve this issue by just make a pivot? Okay, so we will switch the two rows because we see that 1 has a much bigger absolute value than epsilon. So if we switch, and now we carry out the same procedure, and we multiply now the first equation by negative epsilon and add on top. Okay, then we get 0 here, and then we get 1 plus epsilon, and we get 1. And then again, 1 plus epsilon. Epsilon is so small, the computer can only store 1 in it, and then we have this in the end. Okay, so this time actually we'll be solving this, and let's write it out. That will be x1 minus x2 is 0, x2 is 1, and you can easily solve it. So x2 will be 1 and x1 will be 1, and that is the exact solution represented in the computer. Okay, so this is a bit of an extreme example to show you the advantages of pivot, and you can carry out similar calculations to compare the propagation error in the computation. That's what is called when you choose a pivot with a smaller absolute value versus one with a big absolute value. Okay, in the same spirit, but the computation will be a bit more involved to show that. So therefore we just take this extreme example to get the idea. Okay, so that's all for today's lecture, and next time we will look into more issues related to matrices, properties of matrices, and special type of matrices that we will encounter. Okay, so I hope you enjoyed this one, and I'll see you next time.